Hi everybody, this is Mrs. Ellsworth. Do you have any questions about electricity? Such as, how is lightning formed? How does it happen? The utility outlets, how do they work? How do we get our electricity? What type of electricity does a computer take? What about static electricity? Do you have any questions about electricity? If you do, please write them down and we'll discuss them tomorrow. But we're going to move forward here. Electricity. We're going to be talking about Chapter 20. And the whole idea of electricity, we need to go a little bit more towards the basics. How does electricity, how do we get that electrical force? And so when you look at this atom, this is a gold atom, think about how could we get electrical forces? Well, the is to look at the atom and decide how could we get charge from this? Well, it's these electrons on the outside that they're hanging out there, and that makes they're vulnerable from being rubbed off. And if they're rubbed off, or else if they're transferred from one to another, then that is actually a change in charge. And one will become more negative or more positive depending on where those electrons go. And so that creates some different charges. Do you remember what they are? They are negative and positive, or I guess in this case positive and negative charges. Anyways, this attraction of those forces and repelling of them, it creates a force, electrical forces that are caused by either repulsion or else attracting. And so when you have two of the same charge, the electric field is showing a repelling action. And when there are two opposites, they attract. And this is no different when we're talking about electrical forces. They behave the same way that magnets do, with like a north and a south magnet versus two norths. They repel one another, or two souths in that case. In fact, they even create an electric field. And that electric field, you could be talking about this with magnets too if you need something a little more visual, but the electric field has the same exact pattern. And when you put two opposite charges, they show a flow going through them. And when you show two of the same, you get some different kinds of patterns too, and showing repelling. Anyway, there are two main types of electricity: static and current. So here's an example of static. When you get a shock, you get a discharge of electrons going from one source to the other. How about when you go down a slide, you can see this little girl's hair is just sticking up like crazy because she got static electricity from a slide. And here's a big, huge example of static electricity, and that is lightning. Okay, here's now examples of current. Do you notice that there are wires attached to a battery and to some bulbs? And that is current going through there. We've got a loop of continuous electricity current running through it. Okay, here's another example of where you would find current. Heavy current. And then also here is another example of how we'd find current. Do you notice that current has got all wires involved in it? Okay, and that static comes from the root word. The root word comes, stat is like stationary, so it goes from one stationary source to another, and we find a change in charge. So how do we create static electricity? There's three main ways that you can do that. You can charge skipping one object by another, but you can charge it with friction. Okay, rubbing a balloon on your hair, that's a definite way of creating static electricity. Also, you can do it by contact. Okay, hang on to a source that's creating a lot of static electricity, where there's getting a lot of electrons from a source. We'll be doing this with a static generator in our own classroom. Also by induction, you get really, really close, and it creates that static discharge. Okay, so you're transferring charge without contacting something by what's around you. So we also find that with static electricity, we get these discharges. Okay, and what is a discharge? It's really just a spark. It's neutralizing that charge. Okay, and in class we'll be talking about what causes lightning, or I should say, how does lightning occur as best as we know. We'll be watching a video on this, and there's still several things that we don't know about lightning, but basically what happens is that we have some moisture come in the area and some heat, and so we create these big, huge thunderheads, and that they are creating this big anvil-shaped cloud. And inside that anvil-shaped cloud, it becomes to where it's got hail and pieces of snow and moisture that is becoming frozen, and so we're able to rub off the electrons off of those solid pieces. And so it creates a change in charge. At the very top of the cloud, the anvil head, will become really negative. The bottom will become really negative, really positive. And so this then induces some charge from the ground up. It's attracted to that negative charge at the bottom of the clouds. And so what happens, that negative charge, it induces charge from the bottom up. And so that's bringing these positive charges towards the edge of the earth or trees or anything like that. And so now we'll have step leaders come down from the clouds, like right here are some step leaders, and we'll have positive filaments coming up from other sources on the ground, and then they'll come together to form a lightning bolt. If you missed that movie with us, this is a great way to just rewind what I just said and go and catch up with us there. Okay, so moving on, let's talk about current next. Okay, in current we can do some calculating, but we need to know three primary things about current. We need to know about current. Okay, current itself is called, it's defined as the flow of electrons and the flow of charge. And so there's two main types of current, and one of them is DC current, direct current. This where charge only flows in one direction. It flows in a constant, steady stream of electrons moving, and this is often found in batteries, so you probably need to add that to it. Flashlights quite often use batteries. We know that. Sometimes they charge a battery source inside of them, but they've got batteries inside of them, and they have this continuous loop of electrons going through the light bulb. They close that switch and it'll keep on going until, of course, the batteries run out of charge. Okay, and that right there is direct current. Your computers take direct current because AC power is a little bit, well, it's got too much fluctuation in it. And so it needs to have a transformer type of device. You know, it's usually that big, huge square piece on your cord. And even charging your phones, it's got that big transformer piece of it that goes from the plug-in into a USB type port and then into your phone. So those type of things need DC power because it has less fluctuation. Now the second type I kind of alluded to, it is alternating current. It's talking about that flow of electrons that regularly goes back and forth and back and forth, and it alternates. That's why it's called alternating current. Okay, well, the current has to flow through certain things, and we have them flow through conductors, wires. And it's just like it was in our heat unit or in our unit of thermal energy. It flows easily through copper wire, or even if you look up the periodic table right now, you'll notice that it also, in the same family of copper, is also silver and gold. And those are excellent conductors. Very, very good, excellent conductors. I mean, aluminum is a good conductor too, so it's really the metals, just like what we did in our thermal energy unit. Plastics are excellent insulators. They used to have ceramic insulators on fencers and on electric posts, and glass is also another one too. But plastic seems to be a very, very sturdy type of insulator that seems to be used more in place of ceramics. Now, thick wires have less resistance, and if you really think of even like a fire hose compared to a garden hose, how much force of water can come through there, all that pressure that comes through there, you get so much flow through a big, huge fire hose compared to a garden hose, and that is really good at showing how there is less resistance inside of a big, fat hose. And in this case, it's a big, fat wire versus a thin one. In fact, if you think of a light bulb, it's got a very, very small, thin filament of tungsten wire in there, and it gets so much friction in there, it creates so much resistance that it actually glows from all of the friction inside of there. So, let's talk a little bit more about resistance. Okay, it slows the flow of electrons. Okay, we talked about current. Now we're talking about resistance, and I said there was 3 simple or basic concepts that we need to talk about with current. Anyway, so this one right here slows it down. And so again, there are 3 main things that affect the resistance in a wire. One is the thickness of the wire, and I just talked about that. The thinner it is, the more resistance. Also is the length. The longer the length of the wire that you're using, the more resistance in it. When I think of those garden hose again, so flow of water compared to current in a wire, when I stream out a whole bunch of garden hoses, I really don't have much pressure at the end of it because I just have added too much length to it. Okay, temperature is another one. Temperature, when it's really, really warm, it also creates more resistance. Those electrons are moving around a little bit rapidly, but a little bit more disorganized. And so the higher the temperature increases the resistance. Now it can get really cold, and I'm going to talk about a superconductor when we get into classes with some different types of elements in the periodic table. It's quite interesting. Anyway, so moving on to the third piece of information that we need with current, and that would be the voltage. In science, we call it potential difference. This is kind of like talking about that push of those electrons behind it. And so there's only one way that we can measure that when we've got a loop of electricity going, and that's by checking the voltage on one side of an appliance or a light bulb and also on the other, and seeing how much pressure or potential difference that's behind there. And so this helps push the electricity through the light bulb and go back to the battery again. And so, and your batteries are also measured in volts too. Quite often all those little round cylinder batteries are measured 1.5 volts. They're called single cell batteries. Anyway, so now that we've got 3 main components of current, we can also talk about Ohm's law. Okay, and Ohm's law shows a relationship between voltage, potential difference, current, and resistance. And current is shown in this formula here. There's a formula. It's shown with the letter I, and it's measured in the unit amps. Voltage, or potential difference, is with a V, so that's kind of nice. It's the same letter, and it's got the same letter for its unit, which is V for volts. And resistance is with an R in the formula, so that's pretty nice, and this unit is ohms. And I'll show you in the next slide what an omega looks like, which is the abbreviated version of ohms. Anyway, when you cover up the I on this because you're looking for current, it equals V over R. V divided by R. If you're looking for voltage, okay, then you cover up V and you've got I times R. If you're looking for resistance, you cover up resistance and you see that you've got a V over I, or else volts divided by current. And that's 3 different ways of looking at this formula uniquely, and that helps us. Okay, so let's look at these 2 types of problems here. Find the resistance of a circuit that has a 9-volt battery and has the current of 1.2 amps. So we look for an R equals formula with our formula triangle on the last slide, and we'll find R equals V over I, or voltage over current. So find your volts in the problem, and I see we got 9 volts. Okay, and then our current is 1.2 amps. So we divide that and we'll get 7.5 ohms, or omega is the abbreviation for ohms. It is a Greek letter. We're running out of letters, with all the different ones that we look at. Okay, moving on to the next one. Find the voltage of a circuit that has 15 amps and 100 ohms of resistance. Now this one, you cover up the voltage and you see I times R. Okay, and so I is current. Okay, and resistance is 100 ohms, and so you set that up and you multiply them together and you should get just 1500 volts. That's all I got for you, and I'll see you tomorrow, and bring me some questions about electricity.